We have one last section, really short section, that relates to Sn1 and Sn2. This section is just going to be a side-by-side comparison of Sn1 to Sn2. It's a useful section because when you're looking at a substitution reaction, you do need to be able to identify for yourself whether it's going to go by the Sn1 mechanism or the Sn2 mechanism, if nothing else, because the stereochemistry of the products are going to be different. So we're going to compare the Sn1 and Sn2 mechanism in terms of 6 things. The nucleophile, we're going to make a table here. For Sn1 and Sn2. In the Sn2 mechanism, the nucleophile has to be strong. The nucleophile has to have motivation to go after the alkyl halide. The alkyl halide is a stable molecule on its own. So that nucleophile has got to have strong desire to go after that carbon, the carbon which is polarized from the electronegativity of the CX bond, but it's still stable in its own right, and it's not heavily motivated to react. In the Sn1 mechanism, the nucleophile has nothing to do with the initiation of the reaction. So the strength of the nucleophile in Sn1, it doesn't matter. Most of the time, Sn1 reactions are going to have weak nucleophiles, and that's not. The Sn1 mechanism doesn't require a weak nucleophile. It doesn't require anything about its nucleophile. The Sn2 mechanism does require a strong nucleophile, and if you're attempting to do nucleophilic substitution with a weak nucleophile, this is your only option. But you can certainly use a strong nucleophile in an Sn1 mechanism, and it's going to work just fine. The substrate, the alkyl halide, and we talked about how in the Sn1 reaction, because it goes by a carbocation, the substrate has to be tertiary or secondary. You can never do it with primary or a methyl alkyl halide. And in the Sn2 reaction, it's secondary or primary or methyl, CH3X. Either one. Because in this case, you need to have room for the nucleophile to hit the substrate. We talked about the solvent in the two reactions. In the Sn1 and 2 mechanism, in both cases, the solvent has to be polar because you are dealing with polar reactants, polar intermediates, and so the solvent has to be polar to help stabilize and dissolve things. In the Sn1 reaction, the solvent needs to be protic. In the to help stabilize the carbocation. In the Sn2 reaction, the solvent has to be aprotic so that the crazy nucleophile doesn't end up reacting with your solvent instead of with your substrate. And we talked about how commonly we're going to use an alcohol for Sn1, and we're going to use acetone or acetonitrile. For Sn2, those aren't the only solvents that can be used for these reactions, but the most common solvents used for these reactions. We talked about the stereochemistry of Sn1 and Sn2. In the Sn2 reaction, we saw how you get like an umbrella flipping itself inside out, 100% inversion. If you have the possibility of stereochemistry in your product, in your substrate, in your product, you're going to get 100% inversion from R to S or S to R. In an Sn1 mechanism, if you have stereochemistry, you're going to get a racemic mixture 50-50 R and S. We talked about rearrangement. In in the SN2 mechanism, we never saw any rearrangement examples, and that's because it never happens. There's never an opportunity for rearrangement in SN2. You've got it happening all in one step. The nucleophile hitting the substrate and the substrate leaving group popping off all in one step, and there's never an opportunity for anything to rearrange. In the SN1 mechanism, it's possible. Because we go through a carbocation, because the reaction occurs in 2 steps, it stops for a moment at that carbocation, and if it can rearrange, it will. But it's not guaranteed to rearrange. If your carbocation pops off or turns out right away to be a tertiary carbocation, there's no motivation for rearrangement. Or if there's you form a secondary carbocation, but there just simply is no way to form a tertiary, that's fine. The molecule is going to be happy to stay as a tertiary. And then the last thing I wanted to add in here, just one last note, is that we talked about how the SN2 reaction involved 2 molecules colliding. In the SN1 mechanism, we see 1 molecule falling apart. That referring to the leaving group popping off the molecule. And then the thing that confused me that I talked about when we first started this, when I was a student, that the SN2 reaction has 1 step. 2 molecules hit and bam, your product is there. The SN1 reaction has 2 steps. Step 1, molecule falls apart. Step 2, nucleophile attacks. I don't want you to write a summary for this. I don't even think we need a study question for this. And this is the end of the nucleophilic substitution sections.